Okay, we are gonna do a quick review of first order system. And okay, so a first order system is a system that when we take the maximum exponent in the denominator and subtract it of the maximum value in the numerator, we get 1. So examples are just g of s, k of tau x plus 1, where tau is the time constant. Another example could be a of x minus 1 over b of bx squared plus cs plus 1. So here we have 2 minus 1, and this is equals to 1, so it's a first order system. When we have a stepped input, we get a response like this. It looks something like this, where here when we have approximately 63% is where we have tau, and over here when we have 5 times tau is gonna be when we get approximately 99% of the maximum value. And we also know that k is a relation from the output and the input. Okay, and remember tau is just the time constant. So constant, so time constant time response is the better response. So if we have a smaller tau, the system gets to the 63% value faster, so it is a faster response time. Now, now we have also gonna a quick recap of the final value theorem. So it just said that if we want to find the limit of a function in time as time approaches infinity, is the same as having a function in the frequency domain as the frequency approaches 0. But we have to multiply our function by s. So this is our final value 0. Okay, now we can start seeing the controllers. So first we have the proportional controller, that is just a constant value, and here we have our first order system. So what happens when we want to see what is the final value when we have a proportional controller. Okay, so we know that our transfer function is going to be the output over the input. We know that for any system is going to be 1 plus g of x. Okay, so here what we have as g of s is kc tan k over 1 plus st. So for transfer function we're going to have 1 plus, and we're going to have this. So this is we're just following this. So this is, we just need to simplify a little bit, so it'll be a little easier to work with. So we are gonna have kc 1 plus 1 st 1 plus st times 1 plus st plus kc. Okay, and from here we can cancel these two, so we are gonna have kck over 1 plus kck plus st. And now if we factor out the kck both up and below, we factor out kck plus 1. So we have here 1 over 1 plus st over kck plus 1. Okay, we just did it so we can have it in this form. And now we know that for our step input we have such and step input is 1 over s. So our j of s is gonna be equals to 1 over s multiplying this, and for our final value theorem, remember we're trying to find the final value for this, so we multiply by x, so the limit of y of t as t approaches infinity is gonna be the limit as x approaches 0 of x times our y of x, that is this. This is not a 2, this is an x. Okay, so here we have it. So we see that this x and this x is gonna cancel, so these two always cancel when we have a input unit step. And what happens when we have 0 here in x? So this goes to 0. This part will go to 0, and we're gonna have 1 over 1, so it's just 1. So the value is gonna be ck plus 1. So this is our final value for our proportional controller. And for a proportional controller, if we were trying to use a op-amp, it's just gonna be a gain. Now we are gonna do the same for our integral. So here, we're just gonna multiply for our integral. So just like what we did before, we are gonna start by getting our transfer function. That's gonna be x times t1x t1 1 plus st. So it's just multiplying these two together over 1 plus this. Okay, so this is, once you do all the math, this is gonna be k over st1 times 1 plus xt plus k. And if we factor out the k top and the bottom, so we have the form that we're trying to get. So over 1 over k plus 1 st over k plus 1. And now if we apply the limit of y of t as t approaches infinitive, we are gonna get, well, this will become 0, so 0 here, 0 here, so we're just gonna go for 1 over 1, and this is 1, so this is the final value for our integrator controller. And finally, for our proportional integrator controller, because this multiplication and the simplification was a little bit longer, just takes more time. It's not hard, but it just takes time. So I just plugged it in MATLAB and simplify it to get a simpler version of the multiplication, and I got g of x over u of x equals to this. Okay. So now we factor out KC on top and in the bottom. We are gonna get on top, we are going to have TLC plus 1. In the bottom, we are gonna have STC over KKC plus TTC x squared over KKC plus TSC plus 1. And what's gonna happen when we have the limit as y of t approaches infinitive, as t approaches infinitive. Remember, I'm doing this, I'm just jumping the step of multiplying this by u of s, multiplying this by u of s, that is 1 over x, and then saying that this is the limit as s approaches 0 of g of x multiplying by x. Because I am skipping this step because this is 1 over x, and when we multiply 1 by x, they just cancel. So now, as this approaches 0, we're gonna have here the 0, so we're just gonna get 1. This one is gonna go 0, 0, 0, and we're gonna have 1. So 1 over 1 over times 1, so it's just 1. So our proportional integrator controller on our finite value, we're gonna get 1. So this was just a review of different controllers for the when we do the control for our DC machine. Hope this helped.